two probes carrying 69 kilobytes of memory are tumbling through the emptiness between stars at 38,000 miles per hour. They have been making this journey for nearly half a century. The closest neighboring star is still 40,000 years ahead of them. Every passing year, 4 more watts bleed away from their decaying nuclear cores, and one by one their instruments go silent. Before long, the final signal will vanish, and our species will have left nothing operational in that distant dark. What the Voyagers uncovered as they pushed beyond the solar system overturns almost everything we believed. And what lies past that boundary is more unsettling than anyone had dared to imagine. If this is the kind of story that keeps you watching, subscribe and come with us. We start right now. In the summer of 1977, a rare celestial arrangement was slowly assembling itself, one that had not presented itself since the days of Thomas Jefferson. Jupiter, Saturn, Uranus, and Neptune were sliding toward a formation that would permit a single spacecraft, launched at exactly the correct instant, to steal velocity from one planet's gravity and carry it to the next. A chain of gravitational assists across the full width of the outer solar system. That window would remain open for only a handful of years before the planets drifted back into their scattered independent paths. The same opportunity would not reappear for 176 years. The National Aeronautics and Space Administration had been working toward this window for close to a decade. The original vision had been called the Grand Tour, an audacious 4-planet odyssey that Congress eventually cut for financial reasons. What remained was a smaller, less expensive pair of spacecraft, collectively called Voyager. The sanctioned mission covered only Jupiter and Saturn flybys, 4 years of service, and nothing further was promised or expected. Voyager 2 departed first on August 20th from Cape Canaveral in Florida. Voyager 1 followed 16 days later on September 5th, riding a swifter path that would carry it past its counterpart within months. By December, Voyager 1 had already surged ahead. Neither spacecraft was larger than a compact automobile, each tipping the scales at roughly 815 kilograms. They were swathed in thermal insulation, their booms bristling with sensors built to taste, weigh, and hear everything they encountered. The engineers who assembled them at the Jet Propulsion Laboratory in Pasadena, California, understood something the general public never fully grasped. These were delicate machines. Each carried 10 scientific instruments, among them cameras, magnetometers, spectrometers, cosmic ray detectors, and plasma wave sensors, all of which had to perform without fail in an environment that would demolish most off-the-shelf electronics in seconds. Their systems were engineered for a 4-year assignment in the pitiless vacuum of deep space, where temperature oscillates between scorching and near absolute cold based on orientation, where radiation steadily erodes circuits, and where one failed part could end the entire venture. Redundancy was woven through every critical system because no repair mission was ever going to reach these probes. Every fastener, every transistor, every instruction in their code had to perform correctly on the first attempt. There was effectively no margin for failure. The political circumstances of the launch are worth understanding. The Grand Tour had been proposed in the late 1960s as a once-per-generation opportunity to survey all 4 outer planets in a single connected arc. Congress reviewed the budget and recoiled. The full mission was canceled. What NASA salvaged was a pared-down alternative, 2 probes aimed at Jupiter and Saturn, with the slim hope of pushing on to the ice giants if the spacecraft held together. The Voyager program carried a price tag of roughly $865 million, a small fraction of what the Grand Tour would have consumed. Adjusted for inflation, the entire mission that would one day become the most far-reaching act of exploration in human history cost less than many single Earth-orbiting satellites launched decades afterward. Nobody involved in that launch could have guessed what would actually unfold. The 4-year mission would stretch across 5 full decades. The instruments built for planetary flybys would be turned to the task of probing regions no human technology had ever visited. And the 2 modest machines drifting away from Earth would become the most distant objects our civilization had ever sent anywhere, still whispering signals back from the darkness between the stars nearly half a century later. Nobody anticipated them threading through the boundary of interstellar space. Nobody imagined them outlasting the engineers who welded their frames, the scientists who specified their sensors, or the government officials who signed their funding. The Voyager program was supposed to be a brief reconnaissance of the outer planets, a scientific expedition concluded before the decade turned. What it became instead is the farthest, longest, and most unlikely voyage of exploration the human species has ever undertaken. And that story begins with the machines themselves, and an array of engineering choices that should not have held up nearly this long. Remove a modern smartphone and strip it down to a thin slice of its memory. Then divide whatever survives by 3 million. That is the computing power aboard each Voyager. 69 kilobytes of onboard storage, an 8-track tape deck for accumulating science data. Processors running at a fraction of the speed of a pocket calculator you could pick up at any pharmacy. The radio transmitter dispatching data homeward runs at 23 watts, less power than an ordinary refrigerator bulb. From Voyager, one's present distance of more than 15 billion miles, the signal arriving at the 70-meter dishes of the Deep Space Network is so extraordinarily faint that collecting enough of it to power a standard household light for 1 second would require 20 million years of unbroken reception. The engineers at the Jet Propulsion Laboratory in Pasadena assembled a receiving system sensitive enough to fish that whisper out of the background roar of an entire galaxy. Everything aboard the Voyagers was constructed using whatever technology existed in the early 1970s. The onboard computers were written in programming languages that have long since been retired. The storage systems rely on formats that have vanished entirely from Earth. A number of the original engineers have either retired or passed away, and NASA has had to track down aging specialists just to keep alive the communication protocols that no modern system was built to understand. There is no instruction manual for these spacecraft. The working knowledge sits inside the heads of people who were young professionals when the machines launched, and who are now nearing the twilight of their own careers. And yet both spacecraft are still functioning. Voyager 1 has been running without interruption for nearly 49 years. Its components have endured wild temperature swings, ceaseless radiation, micrometeorite collisions, and the slow bleeding of its own power. In 2017, NASA ignited Voyager 1's backup trajectory correction thrusters for the first time since 1980. Those thrusters had spent 37 years dormant in the freeze of deep space, and they fired on the very first try. The scan platform that steers the cameras and instruments locked on both spacecraft at separate moments during their planetary encounters. Voyager 1's seized up in 1978. Voyager 2's froze during its closest pass at Saturn, putting the entire encounter science package at risk. Both times, engineers on the ground improvised, transmitting instructions that took hours to arrive and rotating the spacecraft's orientation to compensate for the hardware that had gone rigid. That is what kept humanity's gaze open at the frontier of the solar system. Machines conceived before personal computing existed, drawing less power than a dim reading lamp, sustained by engineering intuition, layered redundancy, and a run of luck that the people who built them had long ago given up expecting to last. The fact that both probes are still transmitting is either a remarkable tribute to conservative construction or the most extended winning streak in the history of technology. Fastened to the hull of each Voyager is a gold-plated copper phonograph disc 12 inches across, sealed inside a protective aluminum sleeve. A stylus and cartridge come with it. Engraved on the cover is a set of instructions rendered in symbolic notation, describing how to play the record and identifying where in the galaxy the spacecraft originated. 14 pulsars are charted on the surface, each one indexed by its distinctive rotation rate, so that any beings capable of reading the diagram could locate our star within the Milky Way. The contents were assembled by a committee led by Carl Sagan, the planetary scientist and writer who would later become one of the most widely recognized voices in science. Sagan grasped that once the Voyagers cleared the solar system, they would wander through interstellar space for hundreds of millions of years. The records would need to endure that kind of time. Gold does not degrade in vacuum. The engravings will remain readable long after every structure on this planet has eroded to nothing. 115 images are preserved on each record in analog form, using a method that converts visual data into audio waveforms that can be reconstructed and played back by any civilization that works out the instructions etched on the cover. The images document humanity across every stage of life, from infancy through old age. They show the architecture of DNA. They depict continental drift, the chemical makeup of Earth's atmosphere, a woman nursing an infant, a map of the solar system with the spacecraft's path traced across it, mathematical principles ascending from basic counting to more elaborate ideas, along with photographs of cities, terrain, wildlife, insects, and plant life. After the images, the audio section opens with spoken greetings recorded in 55 languages, beginning with Akkadian, the language of ancient Sumer spoken roughly 6,000 years ago, and concluding with Wu, a present-day Chinese dialect. A child says hello in English. A woman extends greetings in Mandarin. Voices in Arabic, Hindi, Bengali, and dozens more each take a moment, their greetings lasting only seconds before the next begins. After the greetings come the sounds of Earth itself, breakers rolling onto a beach, wind threading through forest canopy, thunder moving across a valley, birdsong, the deep calls of whales, the cry of a newborn, a mother's first words to her child, and then 90 minutes of music curated to represent the breadth of human expression, works by Bach, Beethoven, and Mozart, alongside Japanese gamelan, Senegalese percussion, a Navajo night chant, and Chuck Berry's Johnny B. Good. The likelihood that any intelligence will ever come across either Voyager and actually play the record is so vanishingly small it barely counts as a probability. Neither spacecraft is on course for any nearby star. The gulf between stellar systems is so immense that the Voyagers could travel for billions of years without approaching anything close enough for the record to be retrieved. Sagan knew all of this. The committee knew it. They put it on board anyway. The launching of this bottle into the cosmic ocean, Sagan wrote, says something very hopeful about life on this planet. The Golden Record was never truly a dispatch for alien civilizations. It was a letter addressed to ourselves, an assertion that even in the face of the universe's incomprehensible emptiness, human beings would choose to send music. A declaration of identity fired into a void that has no opinion about it, carrying proof that at least one species on one world during one brief instant in cosmic time believed it was worth the effort to announce we existed. The records contain one additional detail that rarely gets mentioned. Somewhere among the sounds encoded on the disc is a compressed recording of Anne Druyan's brainwaves, captured while she meditated on the feeling of falling in love. Druyan, who later married Sagan, had her neural electrical activity recorded and embedded as a 1-hour segment. It was a love letter written in the language of neurons, dispatched into the galaxy on the remote possibility that someone somewhere might one day decode the pattern and grasp what it meant to be a human being in love. The odds of that happening approach zero in any practical sense. The magnitude of the gesture approaches something infinite. But before any of that, the spacecraft carrying those golden records had more immediate work to do, and Jupiter was the first item on the agenda. The largest planet in the solar system was waiting roughly 500 million miles ahead, and what the Voyagers found there was about to unsettle everything. Scientists believed they understood moons, atmospheric storms, magnetic environments, and the scale of destruction a planet could generate in its own vicinity. Jupiter's gravity is a weapon. The planet carries so much mass that its gravitational reach extends millions of miles into surrounding space, bending the trajectory of anything that comes near it. Voyager mission navigators exploited that pull deliberately, steering each spacecraft toward a precisely calculated point in the planet's gravity well that would accelerate the craft and redirect it toward Saturn. The mechanics are straightforward. A spacecraft drops toward a planet, borrows speed from that planet's orbital motion, and gets hurled outward faster than it arrived. A gravitational slingshot. Voyager 1 reached Jupiter on March 5th, 1979, roughly 18 months after departing Earth. Voyager 2 arrived the following July. Both spacecraft gained velocity dramatically during their passes, picking up enough speed to reach Saturn years sooner than their rockets alone could have managed. Without Jupiter's gravitational assist, the Saturn mission would have demanded a far heavier and more costly launch vehicle. Without Saturn's subsequent boost, Uranus was beyond reach for Voyager 2. Without Uranus, Neptune was simply impossible. Every destination on the Voyager itinerary depended entirely on the one before it. Miss the gravity assist window at Jupiter by even a modest margin, and the entire chain collapses. The navigation precision required was within a few dozen miles across distances of hundreds of millions of miles, and the engineers achieved it using computing hardware less capable than a modern wristwatch. But the gravitational slingshot was only the mechanism. The real revelation at Jupiter was what the cameras uncovered during those brief passes. Dozens of interlocking hurricane systems, some rivaling entire planets in diameter, churned through the cloud bands below. The Great Red Spot, a tempest that ground-based astronomers had tracked for more than 300 years, turned out to be a rotating anticyclone of bewildering complexity, perched 5 miles above the surrounding atmosphere. Time-lapse sequences assembled from Voyager photographs showed it consuming smaller storms, tearing them apart and absorbing their rotational energy. 3 previously undetected moons materialized in the imagery, Métis and Adrastea among them. tiny bodies circling Jupiter so closely they had been undetectable from Earth. The planet's magnetic field proved vastly stronger and more expansive than predictions had suggested, generating a radiation environment ferocious enough to threaten the spacecraft's circuitry during close approach. Everything at Jupiter was larger, more savage, and more hazardous than the models had indicated. The radiation situation was genuinely alarming. Jupiter's magnetic field captures charged particles streaming off the Sun and ejected from Io's volcanic activity, accelerating them to enormous energies. The radiation belts produced are the most intense surrounding any planet in the solar system, potent enough to kill an unshielded person in minutes. Both Voyagers transited this environment during their flybys, and the barrage of energetic particles caused electronic glitches across the spacecraft, scrambling data and forcing error correction routines to activate. The cameras produced garbled frames intermittently. Memory cells flipped states without warning. For several tense hours, engineers at the Jet Propulsion Laboratory could not be certain the spacecraft would emerge from the radiation zone with their systems undamaged. They did. The thermal insulation and the shielding wrapped around the spacecraft's most exposed components absorbed sufficient radiation to avoid permanent harm. But the encounter made unmistakably clear that Jupiter is no passive behemoth. It is encircled by a killing field of accelerated particles that would obliterate any unprotected machine or person that ventured inside it. The Voyagers got through by design, by redundancy, and by a degree of luck their engineers preferred not to examine too closely in press briefings. And the greatest shock of the entire encounter was waiting on the innermost large moon, lying in wait for a navigation engineer to catch something unexpected at the edge of a routine photograph. Linda Morabito was a navigation engineer at the Jet Propulsion Laboratory, and her duties during the Jupiter flyby carried little glamour. She processed images to establish the exact position of the spacecraft relative to the moons of Jupiter, a task that demanded brightening faint objects near the margins of each frame. On March 9, 1979, she loaded an image of Io captured by Voyager 1 4 days earlier and spotted something unusual along the moon's horizon. A luminous, curved arc was rising from the surface and climbing hundreds of miles into space. Her immediate instinct was that another moon might be transiting behind Io. The geometry was consistent with that reading. But when she cross-checked the positions of every known moon, none of them occupied that part of the sky. What she was looking at was a volcanic plume, an eruption violent enough to be throwing material 300 miles above Io's surface, visible as a glowing bow against the void. No active volcano had ever been confirmed anywhere in the solar system beyond Earth. The discovery rewrote planetary geology overnight because it demolished a foundational assumption that had underpinned decades of research, namely that moons are geologically inert. The reason Io erupts traces back to Jupiter itself. The giant planet's gravity continuously squeezes and flexes Io's interior as the moon traces its orbit, compounded by the gravitational tugging of the other large moons, which keeps Io's orbit from settling into a perfect circle. This produces a ceaseless cycle of tidal heating that liquefies rock deep within the moon. Io's interior churns without pause, generating 100 times more volcanic output than our own planet. Vast lakes of molten sulfur pool across the surface. Volcanic gas columns rise to elevations that would place them in Earth's upper atmosphere if transplanted here. The surface is completely reshaped every few thousand years by fresh lava, which explains why Io carries almost no impact craters. They get paved over before they have time to accumulate. Scientists had studied our own moon for generations and built their entire model of satellite geology around the image of a cold, motionless body, shaped solely by ancient impacts and gradual cooling. Io demolished that picture in a single sequence of images. A moon could be alive. It could hold a molten interior, an actively repaving landscape, and sufficient volcanic energy to dominate its parent planet's magnetic environment. The ripples ran through all of planetary science. Because if the most fundamental assumption about moons could turn out to be so spectacularly wrong, how many other assumptions about the outer solar system were equally mistaken? The answer, as the Voyagers would proceed to demonstrate repeatedly, was most of them. And the volcanic activity on Io was only the beginning of what it was contributing to the surrounding environment. Io's volcanoes do something that no one had anticipated. They discharge roughly 1 metric ton of sulfur and oxygen into Jupiter's magnetic field every single second. That material does not fall back to the surface. The volcanic plumes launch it high enough for Jupiter's powerful magnetosphere to grab it. Once captured, the atoms become ionized and spread into a glowing ring encircling the planet at the same orbital distance as Io itself. Scientists called it the Io torus, a donut-shaped cloud of ionized particles looping around Jupiter. The torus is immense, stretching hundreds of thousands of miles through space, and it fundamentally reshapes Jupiter's entire magnetic environment. The steady influx of sulfur and oxygen puffs the magnetosphere far beyond what the planet's own rotation would produce alone, making Jupiter's magnetic bubble the largest discrete structure in the solar system aside from the heliosphere itself. The most striking consequence of all this is electrical. The ionized material inside the torus interacts with Jupiter's magnetic field lines to generate an enormous flux tube of electrical current flowing between Io and Jupiter's upper atmosphere. That current carries millions of amperes, enough energy to drive auroral displays visible from the outer edges of the Jovian system. Lightning ignited by this current blooms in the clouds at the point where the flux tube connects to Jupiter's atmosphere above. Io, a moon roughly the size of Earth's own satellite, was single-handedly powering the electromagnetic weather of the solar system's largest planet. One volcanic body was reshaping its parent world's environment on a scale no scientist had conceived as possible. The pairing of Io and Jupiter is among the most extreme examples of planetary codependence ever documented. The moon feeds the planet's magnetosphere with raw material, while the planet tears the moon's interior apart through gravitational force. It is a cycle of simultaneous destruction and renewal that has operated for billions of years, long before any telescope was pointed at the sky, long before any living thing existed to wonder about what was happening out there. The finding forced a complete reassessment of how moons interact with the planets they orbit, and it posed a question that would resonate across the rest of the mission. If Io could be this dynamic, this powerful, this profoundly at odds with expectations, what else in the outer solar system had scientists been wrong about? The answer was waiting one moon over. Voyager 1 was sweeping past Jupiter's night side when its instruments intercepted a radio signal with a recognizable pattern. The signal was a whistler, an electromagnetic wave born from atmospheric lightning that spirals along magnetic field lines and drops in frequency as it propagates. Scientists read the fingerprint instantly. Lightning. Somewhere deep inside Jupiter's cloud layers, electrical discharges were releasing pulses of energy dwarfing anything ever recorded on Earth. Then the cameras confirmed it. Looking back at Jupiter's darkened hemisphere, bright bursts of light were exploding inside the cloud decks, illuminating their tops from below. Each flash lasted only a fraction of a second, but the scale was enormous. Jupiter's lightning fires deeper in the atmosphere than its terrestrial counterpart, at pressure levels that would crush and incinerate any weather system known on our planet. Before Voyager, lightning had been treated as a uniquely terrestrial phenomenon. Theoretical models existed suggesting it could occur elsewhere, but no instrument had ever detected it. Voyager 1 changed that in a single pass. The finding established that the fundamental physics of atmospheric electricity, charge separation and discharge, operates across the solar system wherever the conditions permit it. A new branch of comparative atmospheric science opened that day and has been producing discoveries ever since, from Saturn's lightning storms later examined by Cassini to theoretical frameworks for electrical discharge in exoplanet atmospheres. Jupiter's atmosphere was itself a revelation from close range. The Great Red Spot, which astronomers had tracked through telescopes for more than 3 centuries, proved to be an anticyclone of staggering intricacy. It rotates counterclockwise, rides 5 miles above the surrounding cloud deck, and at the time of the Voyager flyby, measured roughly twice the diameter of Earth. Around it, dozens of smaller storm systems churned through the cloud bands, colliding and merging in configurations that defeated every atmospheric model. The banding itself, those familiar stripes visible through backyard telescopes for generations, turned out to be a system of alternating jet streams, some driving eastward and others westward, with wind speeds hitting hundreds of miles per hour at the boundaries between them. Jupiter was an engine of atmospheric violence, fueled by internal heat it radiates at rates far exceeding what it receives from the distant sun. That internal heat source is one of Jupiter's defining characteristics for understanding the outer solar system. The planet emits nearly twice as much energy as it absorbs from outside. Something inside is still producing warmth, most likely the slow gravitational contraction that has been underway since the planet condensed from the gas and dust disk surrounding the young star 4.5 billion years ago. Jupiter is in a meaningful sense a failed star. It never gathered enough mass to ignite nuclear fusion, but it held on to enough primordial thermal energy to make its atmosphere one of the most energetic environments in our neighborhood. Every storm, every lightning strike, every jet stream, and every fluctuation in its magnetic field traces back to this buried furnace. Remove it, and Jupiter becomes a frigid, unremarkable ball of gas. Keep it, and the planet is a factory of weather systems more powerful than anything else in our region of space. And the Voyagers captured them at resolutions that no ground-based telescope could ever have approached. When both Voyagers passed Europa, the 4th largest of Jupiter's moons, they transmitted images that nobody had prepared themselves for. The surface was almost perfectly unbroken. No impact craters, no jagged ridgelines. Instead, the entire moon was stitched over with a web of dark lines, interlacing fractures spreading across the ice like the veins visible beneath pale skin. On every other body in the solar system, craters pile up over billions of years. A smooth surface carries one meaning: something is eliminating them. On Europa, the explanation appeared to be ice in motion. The surface was frozen water, and the fractures implied the ice was shifting, parting, and refreezing in cycles that could only occur if something liquid persisted beneath. The arithmetic that followed was uncomplicated. Europa orbits close enough to Jupiter to experience tidal heating, the same gravitational kneading that melts Io's interior. Europa's orbit is more nearly circular than Io's, so the heating is proportionally gentler. It is violent enough to liquefy rock inside Io, but on Europa the milder version would be sufficient to sustain a liquid ocean under an ice shell, perhaps 10 to 15 miles deep. If that ocean exists, and subsequent work by the Galileo spacecraft and the Hubble Space Telescope produced strong, supporting evidence that it does, then Europa holds more liquid water than every ocean on Earth combined. Let that settle for a moment. A moon smaller than our own, orbiting a gas giant nearly 500 million miles from the nearest warmth, carrying more water than every river, lake, and sea on the world where life began. An ocean in continuous contact with a rocky floor for billions of years, warmed from below by tidal energy, shielded from the lethal radiation of Jupiter's magnetosphere by miles of ice above it. On Earth, everywhere that liquid water touches rock in the presence of energy, life takes hold. Hydrothermal vents on our ocean floors sustain entire ecosystems that have never received a photon of sunlight, powered entirely by chemical energy seeping from the planet's interior. The question Europa presented, one that remains open today, is whether the same thing has happened beneath that frozen shell. Could organisms be down there in that lightless ocean, drawing sustenance from chemical energy leaching out of the rock below, entirely unaware of the frozen ceiling overhead, entirely ignorant of the universe beyond it? A mission called Europa Clipper launched in 2024 to begin looking, equipped with instruments to measure ice thickness, analyze the chemistry of material venting through surface cracks, and search for any trace of organic molecules that might suggest biological activity. That entire mission exists because of photographs a spacecraft assembled in the 1970s took during a brief flyby more than 4 decades ago. A handful of images captured by a probe built on obsolete technology opened a question about life elsewhere in the universe that a new generation of scientists is still working to answer. Before Voyager arrived, rings were Saturn's trademark. The great system of concentric bands visible through a backyard telescope had been part of the planet's identity since Galileo first observed them in the early 1600s. No other planet was known to possess anything comparable. Ring systems were regarded as a beautiful anomaly specific to Saturn. Then Voyager 1 detected thin, faint rings encircling Jupiter, a planet nobody had ever associated with such structures. The finding was modest measured against Saturn's grandeur, a few narrow bands of dust and debris barely resolved in most frames, but its implications were profound. Ring systems might be a common feature of giant planets rather than a singularity. The hypothesis would be tested at Uranus and Neptune in the years ahead, and both planets validated what Jupiter had implied. Every gas giant in the outer solar system carries a ring system. Each one is distinct from the others. Saturn's rings are brilliant, icy, and breathtaking. Jupiter's are thin, dark, and composed primarily of fine particles. Uranus carries narrow, nearly invisible rings, first detected from Earth when they briefly blocked the light of a background star. Neptune would later show rings of its own, including strange, partial arcs, incomplete ring segments that should have dispersed into uniform bands under ordinary orbital mechanics, but somehow persist, held in position by the gravitational work of small nearby moons. The variety of ring architectures compelled scientists to build entirely new frameworks for how rings form, age, and sustain themselves. Some are ancient, dating back to the earliest epoch of the solar system. Others may be remarkably recent, the wreckage of moons that shattered or comets that wandered too near. The physics governing each system involves gravitational resonances, embedded moonlets, electromagnetic effects, and interactions with the host planet's magnetic field, all working in concert in ways scientists are still unraveling. Every ring system the Voyagers discovered carried the same deeper message. The outer solar system is far more violent, more dynamic, and more structurally layered than the serene and orderly portrait that Earth-based telescopes had painted from billions of miles away. The elegant rings visible through a backyard telescope were, up close, chaotic arenas of colliding particles shaped by invisible gravitational influences, maintained by moons too small to see from Earth, and evolving across timescales ranging from hours to millions of years. And if the rings turned out to be more complicated than expected, the planets inside them were about to prove stranger still. Saturn kept secrets that would occupy scientists for decades after the Voyagers departed. Saturn's rings had served as the planet's signature for 4 centuries. Astronomers had catalogued fewer than 6 broad, distinct bands. The textbook version showed a gorgeous but relatively simple architecture. Several concentric rings divided by gaps, consisting of ice and rock. Voyager erased that picture entirely. When the spacecraft arrived at Saturn in 1980 and 1981, the cameras showed that each broad ring was in reality composed of hundreds of separate ringlets, some so narrow they barely resolved at all. The complexity was fractal. Focus on any region and more detail appeared. Braids wound through the outer F-ring like twisted ribbons of DNA. Spokes, dark radial markings that rotated along with the ring system, appeared and evaporated in ways that contradicted standard orbital mechanics. Gaps that looked empty from Earth harbored faint material, while regions that appeared solid from a distance disintegrated under close examination into thousands of individual strands. 2 tiny moons, Prometheus and Pandora, were found orbiting just inside and outside the F-ring. Their gravitational pull kept the ring confined to its narrow track, a principle scientists called shepherding. The gravity of these small bodies molded the ring material the way riverbanks contain a current, preventing it from dispersing. The concept of shepherd moons was born directly from these Voyager observations and has since been extended to ring systems throughout the solar system. Voyager 2 flew so near the ring plane that its instruments logged hundreds of microscopic impacts every second. Dust grains, particles shed from the rings themselves, hammered the spacecraft at orbital speed. The team watched the impact rate with rising unease. The craft survived undamaged, but the episode demonstrated that ring systems are physically violent environments at the particle level. What appears tranquil and luminous from a distance is up close a bombardment of colliding ice and rock. Saturn's rings turned out to be among the most intricate structures in the solar system, and the moons nested within and around them contributed more surprises. Voyager identified several small moons embedded directly in the ring system, their gravitational signatures carving gaps and wave patterns into the material surrounding them. The moon, Mimas, barely 400 kilometers across, was responsible for the largest gap in Saturn's rings, the Cassini division, through a gravitational resonance that sweeps that region clean as reliably as a broom. Enceladus, another small icy body, presented a surface that was puzzlingly young and featureless, a mystery that would not be explained until the Cassini mission arrived decades later and documented geysers of water ice erupting from its southern pole, evidence of yet another subsurface ocean hidden in the outer solar system. The variety among Saturn's moons was breathtaking. Some were cratered and ancient. Others were smooth and geologically fresh. Hyperion tumbled chaotically along its orbit, its rotation axis wobbling unpredictably, making it one of the most erratically behaved objects ever observed in the solar system. Iapetus was divided cleanly in two, one hemisphere gleaming white and the other coal-black, a bicolored world that resisted simple explanation. Every moon was distinct, every surface narrating a different chapter. The Saturnian system was a miniature solar system unto itself, packing more variety around a single planet than some models had anticipated for the entire outer solar system combined. But the planet's most astonishing moon was not visible to Voyager's cameras at all. It was buried behind an atmosphere denser than our own. Titan is the second largest moon in the solar system, exceeding even the planet Mercury in size. When Voyager 1 swept past it in November of 1980, the cameras found nothing but an opaque barrier. A thick, impenetrable atmosphere of nitrogen and methane haze obscured the surface completely. The moon was wrapped inside an orange shroud so dense that what lay beneath remained entirely unknown for more than 2 decades after the flyby. What the instruments could detect was extraordinary. The atmospheric pressure at Titan's surface exceeded sea level pressure on Earth by 45%. The atmosphere was composed largely of nitrogen, the same dominant gas in our own air, but saturated with methane, and a rich mixture of organic hydrocarbons that produced the characteristic amber color. The surface temperature ran at roughly minus 290 degrees Fahrenheit, cold enough for methane to exist in liquid form rather than as a gas. The inference was staggering. If methane could pool as a liquid under Titan's surface conditions of temperature and pressure, then the same hydrological cycle driving weather on Earth, evaporation, condensation, and precipitation, could function on Titan using methane as the working fluid instead of water. Clouds of methane could build in the upper atmosphere. Methane rain could fall to the ground below. Liquid methane rivers could carve channels across the frozen terrain and accumulate in low-lying lakes and seas. An alien weather engine running on hydrocarbons instead of water, on a moon orbiting a planet more than 1 billion miles from any meaningful source of warmth. Voyager could not verify any of this directly. The cameras were blind behind the orange curtain, but the data was compelling enough to inspire an entire generation of planetary scientists and eventually the Cassini-Huygens mission, which reached Saturn in 2004. The Huygens probe descended through Titan's atmosphere and settled onto the surface, confirming everything Voyager had hinted at. Methane lakes, methane rain, and river channels carved into ice. A landscape shaped by the same processes that sculpt Earth's surface, simply rebuilt using different chemicals. Voyager 1's close approach to Titan carried a significant cost. The flyby trajectory tilted the spacecraft sharply above the plane of the solar system, sending it along a path that could never bend back toward Uranus or Neptune. Prioritizing Titan ended Voyager 1's planetary mission at Saturn. Everything that remained to be discovered at the ice giants now fell to its twin. Voyager 2 was now the sole spacecraft that would ever visit the 2 outermost major planets, and the worlds waiting at the far end of the solar system were stranger than anything either probe had so far encountered. After Saturn, the twin Voyagers diverged forever. Voyager 1 climbed above the plane of the solar system, deflected upward by its close pass at Titan, onto a course that would carry it entirely out of the planetary realm. It would never approach another planet. Voyager 2 pressed on unaccompanied, bearing all of humanity's remaining hope to study the ice giants from close range. Uranus and Neptune reside so far from the inner solar system that they absorb a fraction of a percent of the warmth Earth receives. They circle in perpetual twilight, frigid and unhurried, completing their orbits across decades. Uranus takes 84 years to go around once. Neptune requires 165. These planets were found with telescopes, analyzed from enormous distances, and largely dismissed by mission planners until the Voyager program made reaching them feasible through the linked sequence of gravitational assists. Nobody has gone back since. No mission has been designed, funded, built, and dispatched to revisit either planet in the decades since Voyager 2 passed through. The Cassini mission spent 13 years studying Saturn. The Galileo probe orbited Jupiter for 8. Mars has hosted a continuous fleet of rovers, orbiters, and landers for 4 decades. Uranus and Neptune have each received exactly 1 visit, measured in hours, and no return mission is presently funded or scheduled. Every close-up photograph of Uranus was taken during a single pass in January of 1986. Every atmospheric measurement of Neptune originated from a single flyby in August of 1989. Every documented characteristic of their magnetic fields, ring systems, and complex families of moons traces back to 2 encounters that each lasted less than a day. If Voyager 2 had failed at Jupiter, if its scan platform had permanently seized at Saturn, if any of 1,000 possible failures had occurred across the 13 years separating launch from Neptune, we would know essentially nothing about 2 entire planets within our own solar system. That data is irreplaceable. There are no second chances in the outer solar system. The ice giants matter for reasons that reach far beyond our own system. Surveys of planets orbiting other stars have established that worlds roughly the size of Uranus and Neptune are among the most abundant types of planet in the galaxy. They appear far more frequently than gas giants like Jupiter and Saturn, and far more frequently than small rocky worlds like Earth. Knowing how these planets work, how their atmospheres circulate, what powers their magnetic fields, and how their moon systems develop and evolve is essential for making sense of the data streaming in from exoplanet surveys every year. And yet the only close-up measurements we possess come from 2 flybys performed by a spacecraft that launched before the space shuttle had ever flown. The most common planets in the universe, and we know almost nothing about them. When Voyager 2 reached Uranus in January of 1986, it found a world that overturned every expectation scientists had brought to the encounter. The planet lies completely on its side, tilted 97.8 degrees from the plane of its orbit. Every other planet in the solar system spins roughly upright, its poles oriented more or less perpendicular to the direction of travel. Uranus rolls along its orbital path like a ball rolling down a lane, its poles alternately pointing toward and then away from the distant Sun over the course of its 84-year circuit. The most widely accepted explanation is that an enormous collision early in the planet's history, possibly with an Earth-sized body, knocked Uranus over. But this has never been demonstrated definitively, and the mechanics of such a collision create as many problems as they resolve. How does a planet survive an impact powerful enough to rotate its axis by 90 degrees? What happened to the ejecta? How did the moons wind up orbiting in the same tilted plane? The magnetic field was equally peculiar. On most planets, the magnetic axis and the rotation axis align approximately, both pointing in roughly the same direction. On Uranus, the two are separated by 60 degrees, and the magnetic center is displaced from the geometric center of the planet by a third of its radius. The field does not radiate symmetrically outward. Instead, it sweeps through space as Uranus rotates, like a lighthouse beam tracing wide arcs through the dark. 10 new moons appeared in the data, objects too dim and too small to have been resolved from Earth. Winds howled around the planet at 560 miles per hour. The internal heat output measured 3 times higher than models had forecast, implying an energy source that remains unaccounted for. Everything about Uranus conflicted with the textbook characterization of what a planet should look like. The axial tilt was wrong. The magnetic field was wrong. The temperature was wrong. The moon count was wrong. The ring structure bore no resemblance to anything seen at Jupiter or Saturn. Uranus refused to cooperate with any existing classification, and the data raised far more questions than it resolved. How long has the magnetic field been displaced like this? Is the tilt fixed, or is the field undergoing a reversal? What is generating the winds on a planet that ought to be thermally inactive at this distance from any heat source? All of this came from a single flyby that lasted a handful of hours. No probe has returned since. Everything we know about this planet derives from one pass by one machine, and the planetary science community has been advocating for a dedicated Uranus orbiter mission for decades. As of now, none has been approved or funded. As Voyager 2 swung around to the far side of Uranus, the ring system revealed something unexpected. Photographed from the sunlit side, the rings were narrow, dark, and difficult to capture against the blackness of space. But viewed from the opposite side, backlit by the faint glow of the distant sun, everything transformed. Every dust lane, every streamer of particles that had been invisible from the front suddenly blazed into prominence. Linda Spilker, who had joined the Voyager team as a graduate student in 1977, called the resulting images spectacular. The backlit geometry exposed structures that forward-scattered light had concealed entirely. Thin sheets of dust, gossamer lanes of material orbiting in the gaps between the main rings, all of it abruptly visible simply because the spacecraft had moved to the other side of the planet. The insight extended far beyond ring science. The universe appears fundamentally different depending on the vantage point. The same structure can appear empty from one angle and richly populated from another. Information conceals itself in the direction of observation, and the only method of uncovering it is to occupy a position that no instrument has ever occupied before. By flying behind Uranus, Voyager 2 claimed exactly that position, and the rings disclosed what they had never shown to any telescope on Earth. Uranus had delivered surprises in abundance. A planet knocked onto its side with a misaligned magnetic field. Unknown moons surfacing in frame after frame. Winds that had no business existing given the planet's isolation from any significant heat source. And a ring system that hid its true architecture until someone happened to look at it from the unexpected direction. The encounter lasted less than a day. When Voyager 2 pulled away and aimed its sensors toward the next destination, it left behind a planet that science understood only marginally better than before it arrived. The ice giants remain to this day the least thoroughly studied major objects in the entire solar system. 3.5 years of travel separated the Uranus encounter from the Neptune encounter. During that extended coast, the spacecraft crossed more than 1 billion additional miles of vacant space. The instruments operated in a reduced power configuration, gathering baseline readings of the solar wind and magnetic environment, but generating little that reached public attention. The team at the Jet Propulsion Laboratory invested that interval planning the Neptune encounter with obsessive precision, knowing this would be the final planetary flyby, the last opportunity to photograph an unexplored world before the spacecraft passed into the featureless expanse beyond the outermost planet. The engineering obstacles at Neptune were formidable. The planet sat nearly 3 billion miles from Earth. At that distance, the feeble sunlight was 900 times fainter than at Earth, which meant the cameras required far longer exposures to produce anything usable. Longer exposures meant the spacecraft's own motion would smear the photographs unless something compensated for it. Engineers devised a technique called image motion compensation, rotating the entire spacecraft at a controlled rate during each exposure to track the target, essentially panning the camera the way a sports photographer tracks a moving subject. The method had never been executed at this level of precision. It worked. Communication delays had lengthened to more than 4 hours each way, making real-time course adjustments impossible. Every maneuver had to be scripted in advance, uploaded to the spacecraft's computer, and executed entirely on its own. If something went wrong during closest approach, the team on Earth would not learn about it for more than 4 hours, and any corrective command would require another 4 hours to arrive. The Neptune encounter was, in every functional sense, a robotic operation performed without human oversight at the critical moment. The preparation justified itself. The image motion compensation technique produced photographs of remarkable sharpness, resolving details on Neptune and its moons that ground-based instruments could never have approached. The communication protocols, tested and refined across 12 years of progressively more distant operations, held without breaking despite the 4-hour signal lag. Every pre-programmed sequence executed correctly, and the spacecraft carried out the most intricate autonomous operations of its entire mission without a single intervention from the ground. When the data began arriving at the Jet Propulsion Laboratory, the quality exceeded every expectation. Neptune, when Voyager 2 arrived, did not disappoint. It terrified. Voyager 2 reached Neptune on August 25, 1989, after 12 years of travel and more than 4 billion miles from its origin. This was the final planetary encounter of the Voyager program, and the engineering team understood they would not get another opportunity at an ice giant. They extracted every possible reading from the spacecraft's instruments during the narrow window of close approach. The first major finding was a storm. A vast, dark oval quickly christened the great dark spot occupied Neptune's southern hemisphere, rotating counterclockwise within bands of bright methane cloud. The storm was approximately the size of Earth on a planet so far from the Sun that the energy arriving from sunlight was negligible. A storm of that scale should not have been physically possible there. Nobody had an explanation for where the energy came from. Then the wind measurements arrived. 1,500 miles per hour. The fastest winds ever recorded anywhere in the solar system. The strongest hurricanes on Earth sustain winds of roughly 200 miles per hour. Neptune's winds were nearly 8 times more powerful, screaming around the planet with enough force to strip matter from the tops of the clouds and fling it into the upper atmosphere. The only explanation the scientists could assemble pointed inward. Neptune radiates 2.5 times more energy than it receives from the distant sun. Something in its interior, possibly the radioactive decay of heavy elements deep inside the core, or the slow contraction of the planet's own mass, is generating heat that drives atmospheric circulation far beyond what external energy alone could ever sustain. The planet runs on its own internal fire. Neptune has no solid surface in any conventional meaning of the phrase. No ground to walk across, no bedrock to drill into, no terrain to interrupt the wind. The atmosphere continues downward without interruption, growing steadily denser and hotter with depth. There is no sharp transition between gas and liquid. The change is gradual, a compression that works hydrogen, helium, methane, and ammonia through states of matter that simply do not occur naturally anywhere on Earth. At extreme depths, the temperature and pressure may be sufficient to compress carbon into diamonds that drift slowly down toward the core like rain. Above all of this, the winds encounter nothing in any direction but more atmosphere. No obstacles to deflect them, no surface friction to slow them, no landscape to break the flow. The result is the most violently turbulent atmospheric environment in the known solar system, wrapped around a planet that barely collects enough light from its star to cast a shadow. Neptune's largest moon turned out to be one of the most astonishing objects Voyager encountered across the entire mission. Triton is among the coldest places ever measured in the solar system. Its surface temperature holds at 37 Kelvin, roughly minus 391 degrees Fahrenheit. At that temperature, nitrogen itself crystallizes into a solid. The entire moon is sheathed in a thin layer of nitrogen ice, with patches of frozen methane and carbon monoxide lending a pinkish tone to the southern polar regions. Voyager 2 swept past Triton during the Neptune encounter, and the images that returned were unlike anything the mission had previously produced. The surface appeared geologically young, carrying very few impact craters. Dark, fan-shaped deposits streaked across the southern polar cap, each one oriented in the same direction as though laid down by a prevailing wind, like paint brushed across ice. Then the team found the geysers. Active eruptions were punching through the frozen surface, driving columns of nitrogen gas laden with dark particles 5 miles into the thin atmosphere above. For comparison, Old Faithful Geyser at Yellowstone National Park reaches a maximum height of about 200 feet. Triton's geysers were 25 times taller, blasting frozen material from a surface so cold that the nitrogen feeding the plume had been a rigid block of ice moments before the eruption. The energy source behind this activity is believed to be the feeble trickle of sunlight reaching Neptune's distance, which sounds paradoxical on a world where the temperature never climbs above minus 300 degrees. But the mechanism is precise and elegant. Even at Neptune's immense remove from the sun, a thin stream of radiant energy can penetrate the transparent nitrogen ice and reach darker particles of dust or organic material trapped within it. These dark inclusions absorb light more efficiently than the surrounding clear ice and warm the gas locked around them. The heated gas builds pressure below the ice until the cap fractures and the gas erupts outward in an explosive release. The dark streaks visible on the surface are the fallout deposits from these eruptions. particles carried downwind by Triton's tenuous atmosphere and scattered across the frozen landscape like volcanic ash. Triton is one of only 3 bodies in the solar system known to carry an atmosphere consisting primarily of nitrogen. The other 2 are Earth and Titan. The parallel is striking. Nitrogen-dominated atmospheres appear on a warm, wet world teeming with life, on a moon soaked in hydrocarbon rain, and on a frozen rock hovering near absolute zero at the outermost edge of the known planetary system. The chemistry producing these atmospheres differs in each case, yet the outcome is eerily consistent. This cold, remote moon circling a planet that receives almost no usable energy from its star has an atmosphere, active weather, and functional geology powered by processes so subtle and fragile that scientists are still debating exactly how they operate. Linda Spilker had been with Voyager since 1977. By the time the spacecraft reached Neptune, she had spent 12 years watching data descend from the outer solar system onto screens at the Jet Propulsion Laboratory. During closest approach, the data arrived on small monitors, building up row by row, each line of pixels revealing a surface or feature no human eye had ever observed. She placed a sleeping bag under her desk. The images arrived at all hours, and she was not willing to miss any of them. Triton's surface assembled itself on her screen in real time. Pink nitrogen ice, dark radiating streaks from active geysers. A landscape shaped by forces operating at temperatures that would freeze a room solid in seconds. "I remember watching those first pictures come back," she said afterward. "It was just so exciting to know I am seeing data from this world that we really do not know much about." The Neptune encounter was the emotional summit of the planetary mission. 12 years of travel, 4 giant planets, more discoveries than any mission in the prior history of space exploration. Volcanic moons discharging material into space at a metric ton per second. A possible ocean under miles of ice that might conceal life. Storms with winds 8 times stronger than the worst hurricanes on Earth, powered by internal heat on a planet that receives almost no energy from its star. Rings encircling every giant planet, each system more intricate than the last. Geysers erupting 5 miles high from surfaces so cold that nitrogen forms a solid. An atmosphere denser than our own wrapped around a moon smaller than Mercury. And dozens of previously unknown moons, each a world unto itself, catalogued during flybys, measured in hours that will not be repeated within our lifetimes. Then it ended. Voyager 2 swept past Neptune and kept going, pushing outward into the vacancy beyond the final major planet. The photographs stopped coming. The cameras would soon be powered off for good. The next phase of the mission would carry no images, no dramatic visual disclosures, no surfaces to map. The Voyagers were entering a region where the only meaningful data was invisible. Magnetic fields, charged particles, plasma oscillations. The age of pictures was ending and the age of silence was beginning. But before the cameras went permanently dark, Carl Sagan had one final request. He had been pressing it for 7 years, and this time NASA was finally prepared to say yes. Ed Stone had served as the Voyager project scientist since 1972, 5 years before either spacecraft launched. He would hold that role for more than 50 years, guiding the mission through every planetary encounter, every instrument failure, every funding battle, and every moment of discovery. When Triton's geysers appeared on the monitors, Stone was in the room. When the heliopause was finally confirmed, Stone was there. His career and the mission had become a single thing. Stone understood something about Voyager that most observers overlooked. The mission was not merely about the data it gathered. It was about what happens to a species when it first sees its own neighborhood from the outside. Every photograph, every temperature reading, every magnetic field measurement changed how scientists perceived the solar system, and, through them, how everyone else understood their place within it. Stone once described the experience of the planetary encounters as receiving a gift. Each flyby delivering information so unexpected and so beautiful that the scientists receiving it felt as though they were opening something precious and irreplaceable. When the cameras powered down, Stone was there to authorize the sequence. When, engineers debated whether to gamble by disabling the voltage regulator. Stone supported the decision. He would remain at his post until his death in 2024. At 88, he had overseen the longest, most distant voyage of exploration in human history, from the launch pad at Cape Canaveral to the threshold of interstellar space, across a span of 47 years. And he did it with a quiet dedication and sustained enthusiasm that never diminished across 5 decades of discovery, failure, near catastrophe, and triumph. The mission outlasted many of the people who created it. The spacecraft is still moving. The data is still arriving. And somewhere inside the Jet Propulsion Laboratory, a new generation of engineers maintains the link to machines built before they were born, using protocols developed by colleagues they never worked alongside, sustaining a mission that was supposed to conclude after 4 years. For 7 years, the answer had been no. Carl Sagan had first proposed the idea in 1981, shortly after Voyager 1 completed its Saturn flyby and began climbing above the plane of the solar system. The concept was almost disarmingly simple. Before the cameras went dark permanently, rotate Voyager 1 and photograph Earth from the edge of the solar system. A portrait of our planet from a distance so vast that the resulting image would show essentially nothing. A dot, perhaps smaller than a dot. NASA leadership at the Jet Propulsion Laboratory declined on practical grounds. A planet occupying less than a single pixel held no scientific value. Powering up and carefully aiming the cameras would consume time and resources better directed elsewhere, and there was a genuine risk that pointing the optics so close to the sun might permanently damage them. The project leadership would not accept that trade. Sagan proposed it again and again across 7 years. His argument was never grounded in science. He wanted humanity to see itself from the outside. The Apollo program had produced the famous Earthrise photograph, an image of our planet as viewed from lunar orbit that had reshaped the way a generation understood their home. Sagan believed a photograph taken from 100 times farther away could do something even more profound. It could show a civilization that had spent its entire existence on a single world exactly what that world looks like from the vantage point of the cosmos. A speck, a grain, a mote of dust drifting through an ocean of void. Support within the Voyager team gradually coalesced around Sagan's idea. Technical resources were assembled. Political obstacles were worked through. The observation was officially scheduled. On February 13, 1990, Voyager 1 warmed its cameras for 3 hours and prepared to look back over its shoulder for the first and last time in its operational life. The spacecraft was nearly 4 billion miles from Earth when it began its sequence. The science platform rotated to point the cameras at Neptune first, then Uranus, then Saturn, Mars, Jupiter, and finally Earth and Venus. 60 frames in total, composing what would come to be called the family portrait of the solar system, the first view of our entire planetary neighborhood as seen from the outside. Earth showed up in a single narrow-angle frame, a faint, pale smear of light, less than a pixel wide, caught inside a diagonal band of scattered sunlight. The image was recorded at 4:48 Greenwich Mean Time on February 14, 1990, Valentine's Day. 34 minutes after the shutter closed on that final frame, the cameras were powered down permanently. They have never operated since. It took weeks for all the image data to arrive. The signal traveled at the speed of light across nearly 4 billion miles of empty space, and the available bandwidth was achingly limited. The complete download required 4 separate sessions with the Deep Space Network and was not finished until May 1, 1990. Candace Hansen Koharchek, one of the scientists who had designed the command sequence that controlled each exposure's timing and duration, was at a computer inside the Jet Propulsion Laboratory, with the blinds drawn when she first noticed the dot. A speck suspended within a diagonal streak of scattered light, barely distinguishable from the noise surrounding it. It was just a little dot, she said, about 2 or 3 pixels in size, nothing very large. I still get chills down my back because here was our planet bathed in this ray of light, and it just looked incredibly special. Sagan saw the image and composed the words that would accompany it for every generation afterward. Look again at that dot. That is here. That is home. That is us on it. Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives there. The aggregate of all our joys and suffering, thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every hopeful child, every mother and father, every inventor and explorer, every teacher of morals, every corrupt politician, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. The pale blue dot remains the most distant photograph of Earth ever taken. Voyager 1 was 4 times closer to our planet at the moment of that photograph than it is today. The image has never been repeated. No operational spacecraft is positioned to take a comparable one, and none is being planned. The pale blue dot stands in isolation, a single frame captured during the final 34 minutes of a camera's active life, depicting a world that appears so diminished and so fragile that every border drawn across its surface, every war fought over its territory, every dispute over its resources becomes, from that distance, simply absurd. Sagan's words moved into the culture and stayed. They are recited in classrooms, reproduced on posters, and engraved on commemorative plaques. The image has circulated millions of times, and yet its power rests on a paradox. The photograph contains almost nothing. The planet is barely present. The frame is overwhelmingly empty space with a single, nearly undetectable dot. That is precisely the point. The less you see, the more completely you understand. With the cameras off, both Voyagers went blind. The instruments still running measured forces invisible and unphotographable, the magnitude and orientation of magnetic fields, the density and velocity of charged particles, the frequency of plasma oscillations propagating through the surrounding medium. The spacecraft could no longer observe. They could only listen and register. That transition, which happened in 1990, fundamentally altered the character of the mission. The planetary phase had been visual, immediate, and dramatic. Images arrived on screens within hours of being captured, and the world participated in the excitement of discovery in real time. The interstellar phase was invisible, incremental, and measured across years. Shifts in the surrounding environment unfolded over distances so enormous that establishing a trend could require a full decade. The drama migrated from photographs to numerical datasets, from surfaces to fields, from the spectacular to the imperceptibly subtle. Both spacecraft pressed on at their cruising velocities. Voyager 1 at roughly 38,000 miles per hour. Voyager 2 at approximately 35,000. Their instruments registered a slow and steady weakening of the solar wind, the stream of charged particles continuously blowing outward from the sun. Meanwhile, cosmic rays originating from beyond the solar system, particles accelerated by distant supernovas and other violent galactic events, intensified year by year. The boundary between our star's domain and true interstellar space was somewhere ahead, but nobody knew precisely where. Theoretical models put the heliopause, the point where the solar wind's outward pressure equals the inward pressure of the interstellar medium, somewhere between 80 and 150 astronomical units from the Sun. 1 astronomical unit is the Earth-Sun distance, roughly 93 million miles. The model uncertainty alone spanned a range of more than 6 billion miles. The only way to locate the boundary with certainty was to cross it and read what the instruments reported. Both Voyagers drifted outward year after year, transmitting numbers that shifted by tiny fractions. The waiting extended for more than 2 decades. Voyager 1's cameras had been dark for 22 years before the first definitive signs of the boundary region appeared. The termination shock arrived first. This is the zone where the supersonic solar wind blasting outward at hundreds of miles per second abruptly drops below the speed of sound as it meets the resistance of interstellar gas pressing inward. Think of it as the place where a powerful river current finally meets the open ocean and decelerates suddenly, churning into turbulence. Voyager 1 crossed this threshold in December of 2004 at a distance of 94 astronomical units from the Sun. Voyager 2 followed in 2007, crossing at 84 astronomical units, roughly a billion miles closer. The difference in crossing distances carried significant information. The heliosphere, the protective bubble of solar wind enveloping our star system, is not a sphere. It is asymmetric, squeezed inward on one side by the interstellar magnetic field and pushed outward on the other. The boundary shifts, driven in and out by variations in solar activity across the roughly 11-year solar cycle. The Voyagers crossed it at different positions, under different conditions, at different distances, giving scientists their first direct evidence that the bubble's shape is uneven and dynamic rather than smooth and stable. Beyond the termination shock lies the heliosheath, a broad and turbulent region where the slowed solar wind piles against the interstellar medium ahead of it. Both Voyagers spent years navigating through this zone, and the data they returned documented conditions that no model had accurately anticipated. Plasma temperatures ran higher than expected in certain areas. Flow patterns behaved erratically, moving in directions that conflicted with theoretical calculations. The magnetic field fluctuated in ways suggesting the heliosheath was far more chaotic than anybody had imagined. Voyager 1 eventually entered a zone within the heliosheath where the outward radial flow of the solar wind fell to nearly zero. Scientists labeled it the stagnation region. The plasma appeared to have simply ceased moving outward, as though it had encountered an invisible wall. Engineers on the ground commanded the spacecraft to roll 90 degrees and hold that orientation for several hours, sampling in a new direction to test whether the flow had been deflected sideways rather than stopped. It had not. The flow had ceased entirely. The wind that had blown outward from the sun for billions of years had exhausted its momentum. Ahead lay the heliopause itself, the final membrane separating the solar bubble from the open galaxy beyond it. And when the crossing came, it would look nothing like what the theorists had forecast. August 25th, 2012. 121.6 astronomical units from the Sun, roughly 11.3 billion miles from Earth. On that date, Voyager 1's cosmic ray instrument registered a sudden sharp rise in galactic cosmic ray intensity. High-energy particles generated by supernova explosions and other violent phenomena beyond the solar system. Simultaneously, the lower energy particles originating from within the heliosphere fell to undetectable levels. Solar particles vanished. Galactic particles surged in. The spacecraft had punched through the heliopause and entered interstellar space. It was the first time any human-made object had crossed that threshold. The first time any instrument had directly sampled the medium filling the space between the stars. This should have been an immediate and thunderous announcement, a historic milestone confirmed and broadcast in real time. Instead, the Voyager science team paused. For 13 months, NASA said nothing publicly. The silence was intentional. The problem was the magnetic field. Every theoretical model had predicted that crossing the heliopause would produce a sharp rotation in the magnetic field's direction. Inside the heliosphere, the field is sculpted by the Sun's rotation into a spiral extending outward. Beyond the heliopause, it should realign with the galactic magnetic field, which points in a completely different direction. Voyager 1's magnetometer recorded an increase in field strength at the crossing point, but the direction barely shifted. The field on the other side looked nearly identical to the field inside the bubble. Stamatios Krimigis, one of the mission's principal investigators, later observed that nature had apparently not read the theorists' papers and did not know it was supposed to rotate the magnetic field. The remark captured the scientific community's exasperation, the most consequential boundary crossing in the history of exploration, and the universe declined to behave as the textbooks predicted. The data was ambiguous enough that a number of scientists argued Voyager had not actually passed through the boundary at all. Perhaps it occupied some intermediate zone, a region still partially connected to the heliosphere from the other side. The debate was pointed and unresolved for months. The spacecraft's plasma science instrument, the one device that could have settled the argument definitively by measuring the density of the surrounding medium, had been dead since 1980. It failed during the Saturn flyby 32 years earlier, and there was no mechanism to repair it from 15 billion miles away. What ultimately confirmed the crossing came from an instrument that had been silent for 7 years, and the proof arrived 13 months after the fact, carried by the fading echoes of a storm that had erupted on the surface of our star. In March of 2012, a burst of solar activity had driven a wave of charged particles outward from the Sun. That wave traveled through the heliosphere and the turbulent Helios heath at a finite speed until it reached Voyager 1's location 13 months later in April of 2013. When the wave struck, it collided with the interstellar plasma surrounding the spacecraft and set the medium vibrating. Electrons in the plasma began oscillating at frequencies directly tied to the local gas density. Those oscillations generated radio waves that Voyager's plasma wave instrument was able to detect. The instrument had recorded nothing for 7 years. Then it lit up entirely. The oscillation frequency told scientists precisely what they needed to know. The electron density at Voyager's position was approximately 40 to 50 times greater than the density inside the Helios sheath. This was the cold, dense interstellar plasma that should exist beyond the heliopause. The interstellar medium had rung like a struck bell in response to a pressure wave that originated at the Sun and traveled billions of miles to reach the spacecraft. A review of earlier archival data uncovered a fainter set of oscillations from October and November of 2012, likely produced by prior solar activity. Working backward from those oscillations, their onset coincided precisely with the August 25th date, when the cosmic ray measurements had shifted so dramatically. The case was complete. On September 12, 2013, more than a year after the crossing itself, NASA announced that Voyager 1 had entered interstellar space. The spacecraft had become the first human construction to reach the medium between the stars. The confirming signal had traveled for over 16 hours at the speed of light to reach Earth, and then the analysis had consumed another 13 months of scientific deliberation to complete. The galactic environment Voyager had entered was expected to be quiet, uniform, and featureless, a serene backdrop against which the heliosphere floated. That expectation collapsed almost at once, and what the probe found on the other side would force a fundamental rethinking of the physics governing the space between the stars. In 2021, a doctoral student at Cornell University named Stella Koch-Acker was reviewing data transmitted by Voyager 1 from beyond the heliopause. Between the sporadic bursts of plasma oscillation triggered by solar storms, she found something concealed in the background noise. A faint, constant, narrow-band signal, a persistent hum generated by the interstellar gas itself. The plasma wave instrument had been registering it the entire time, but the signal was so subdued that it required careful filtering to separate it from the surrounding noise floor. When she isolated it, the result was unmistakable. A continuous monotone drone, steady and unvarying, produced by the natural oscillation of electrons throughout the interstellar medium. It is very faint and monotone because it is confined to a narrow frequency band. Koch-Acker explained that what they were detecting was the faint, persistent hum of interstellar gas. James Cordes, the senior author on the published study, described the sound using an image that captures its essence cleanly. The interstellar medium is like a quiet or gentle rain. In the case of a solar outburst, it is like detecting a lightning bolt in a thunderstorm and then returning to the steady, quiet rainfall. The finding means that interstellar space has a voice. The void between stars generates a constant low tone at a frequency corresponding to roughly 1 electron per cubic centimeter. A density so thin that a room-sized volume of this space would hold fewer particles than the fingers on one hand. Yet those particles oscillate. And Voyager was the first instrument ever constructed sensitive enough to hear them. To appreciate just how thin this is, consider that the air you are breathing contains roughly 25 billion molecules per cubic centimeter. Interstellar space holds 1 electron in the same volume. The ratio between the density of Earth's atmosphere and the density of interstellar plasma is roughly the ratio between an ocean and a single drop of water thinned across a continent. The space between stars is emptier than the finest vacuum any laboratory on Earth has ever produced. And yet even this almost nothing vibrates at a frequency a sufficiently precise instrument can register. The hum is real. The emptiness is singing. The discovery also indicated that there is more low-level activity in the interstellar medium than scientists had assumed. The space between stars is not an inert vacuum. It is a tenuous but genuinely active environment, shaped by magnetic fields, cosmic rays, and the distant gravitational and radiative influence of every star in the neighborhood. The quiet, persistent hum of plasma oscillation has continued unbroken across the centuries and millennia. A background sound playing since long before our star system existed, and one that will continue long after it disappears. Voyager was listening to the galaxy breathing. 6 years after Voyager 1, its twin followed it through the boundary. On November 5, 2018, Voyager 2 crossed the heliopause at approximately 119 astronomical units from the Sun, roughly 2.5 astronomical units closer to the Sun than its siblings crossing 6 years before. That difference in distance was meaningful. It demonstrated that the heliosphere is not symmetric. The interstellar magnetic field presses harder against the southern face of the stellar bubble, compressing it inward. Voyager 2 had approached from below the ecliptic plane, traveling in a different direction from Voyager 1, and the boundary it crossed was measurably nearer to the Sun. 2 crossing points separated by 6 years, in different directions at different distances. Together, they gave scientists the first 3-dimensional picture of where the heliosphere ends and the galaxy properly begins. The most valuable aspect of Voyager 2's crossing was a piece of hardware that had failed on Voyager 1. Since 1980, Voyager 1's plasma science instrument had been dead, having failed during the Saturn flyby, which was precisely why the 2012 heliopause crossing had been so difficult to confirm. Scientists had spent 13 months in disagreement over whether the boundary had genuinely been breached, because the instrument that would have settled the matter was not functioning. Voyager 2's identical instrument was still working. For the first time, scientists could directly measure the temperature, density, and velocity of interstellar plasma at the precise instant of crossing. The data showed a sharp, definitive jump in plasma density, confirming that the heliopause is a real and persistent boundary separating 2 physically distinct environments. On one side, hot and tenuous solar wind plasma. On the other, cold and dense interstellar gas. The transition occurred over a distance so short that the spacecraft crossed it in less than a day. Every observation was consistent with Voyager 1's crossing 6 years earlier. The heliopause was real. It was durable, and both spacecraft were now on the far side, traveling through the medium that fills the space between the stars. The 2 crossings, considered together, represent one of the most significant achievements in the history of space exploration. 2 machines launched in 1977, designed for a 4-year mission to Jupiter and Saturn, had survived long enough to reach and penetrate a boundary that humanity had theorized about for generations, but never directly measured. The data from those crossings will inform models of stellar physics, heliospheric structure, and interstellar medium chemistry for generations to come. Every future spacecraft dispatched beyond the solar system will calibrate its instruments against the baseline the Voyagers established. That baseline was set by 2 probes running on technology that would have been considered obsolete before the personal computer became a household appliance. Scientists had anticipated that the region beyond the heliopause would prove quiet. A uniform expanse of cold interstellar gas gently permeated by galactic cosmic rays and threaded with magnetic fields oriented in a fixed direction. The kind of environment where measurements would be stable and uninteresting. A calm sea following the turbulence of the Helios Heath. The reality was considerably more complicated. After entering interstellar space, Voyager 1 was expected to settle into steady and unremarkable data collection. The galactic medium was supposed to be calm, a cold and still bath of gas and weak magnetic fields without meaningful variation on the scale of astronomical units. Instead, the spacecraft kept detecting intermittent spikes in cosmic ray intensity, arriving like tsunamis, sudden rises that built rapidly and then receded over weeks or months, disrupting the expected baseline and generating data that no existing model could fully explain. These bursts were not random. They correlated with solar activity, with storms that had erupted on the face of the sun months or years earlier, and whose effects had propagated outward at finite speed through the heliosphere, before crashing into the interstellar medium beyond the boundary. The implication was profound. The sun's reach extends beyond its own bubble. Pressure waves generated by solar flares and coronal mass ejections do not terminate at the heliopause. They cross it, and they disturb the interstellar environment on the far side. The boundary is not a wall. It is a membrane permeable to certain forms of energy. A region that scientists had assumed was isolated from the sun turned out to still be connected to it, still shaped by its outbursts, even at distances exceeding 11 billion miles. In October of 2020, both Voyagers registered an unexpected increase in the density of the interstellar plasma itself. The finding warranted formal scientific publication. According to the researchers, the density gradient was a large-scale feature of the very local interstellar medium, implying that as the spacecraft move outward, the space around them is gradually becoming denser and more populated with the raw material of the galaxy. Nobody had predicted this trend. Models assumed uniform density beyond the heliopause, with significant variations occurring only across distances of light years. The frontier is restless, structured, and still connected to the star that dispatched these machines nearly half a century ago. The Voyagers are mapping a galactic neighborhood that turns out to be more complex, more active, and more surprising than anyone imagined. And they are doing it with instruments that are running out of time. The unexpected richness of the interstellar medium carries implications far beyond the Voyager mission itself. If the space between stars is not uniform, if it contains structures and density gradients and pressure pulses on scales that no current model accounts for, then the environment through which our entire solar system moves is more textured and variable than anyone had assumed. The heliosphere is not drifting through a still and featureless bath. It is plowing through a medium that actively pushes back, that fluctuates in density and orientation over distances of only a few astronomical units, and that preserves the imprints of events, supernova explosions, stellar winds, collisions between interstellar clouds that occurred millions of years ago and thousands of light years away. The Voyagers are sampling this medium in real time from two separate positions with instruments that were never designed for this purpose but are performing it regardless. Every transmission they send back adds another measurement to a map that no other instrument in existence can contribute to. When they go silent, that map will freeze permanently, and the next direct measurement of interstellar space will wait until another spacecraft follows the same path decades or centuries from now. Each Voyager carries 3 radioisotope thermoelectric generators, devices that convert the thermal energy of decaying plutonium-238 into electrical current. The plutonium was loaded in 1977 and has been decaying without interruption ever since. Each year, the generators produce approximately 4 fewer watts of electricity than the year before. The decline is slow, predictable, and completely irreversible. Nothing can stop it. Nothing can replace the fuel. The output will continue falling until the generators can no longer sustain any instrument aboard either spacecraft. At launch, each Voyager's generators produced roughly 470 watts. Today, each spacecraft generates approximately 249 watts. A standard kitchen toaster draws between 800 and 1,500 watts. The complete electrical budget for humanity's most distant exploration mission is less than the power consumed by the smallest appliance in most homes. The instrument shutdowns have been proceeding for decades. During the planetary encounters, all 10 science instruments on each spacecraft operated simultaneously, drawing current for cameras, spectrometers, photopolarimeters, and charged particle detectors. As the planetary mission concluded and instruments became unnecessary for the interstellar phase, the engineering team switched them off one by one. The cameras were first. The ultraviolet spectrometer followed in 1990. Additional instruments were retired over the subsequent years as priorities evolved and the power margins tightened further. By February of 2025, the shutdowns had reached the core instruments that had been measuring the interstellar environment itself. On February 25th, NASA powered off Voyager 1's cosmic ray subsystem, the very instrument that had played the central role in detecting the heliopause crossing 13 years earlier. 1 month later, on March the 24th, Voyager 2's low-energy charged particle instrument went dark. 3 science instruments now remain active on each spacecraft. On Voyager 1, the magnetometer, the plasma wave subsystem, and the low-energy charged particle instrument, which is scheduled for shutdown in 2026. On Voyager 2, the magnetometer, the plasma wave subsystem, and the cosmic ray subsystem, also slated for deactivation in 2026. After that, both spacecraft will operate with only 2 instruments each. The minimum possible toolkit for studying the space between the stars. Every other measurement capability the mission once possessed, the cosmic ray counts, the charged particle analysis, the plasma density readings, will be gone. The remaining instruments will tell scientists the local magnetic field strength and the nearby electron count. That is all. Everything else about the interstellar medium, its temperature, composition, flow direction, and interaction with the solar wind now far behind, will have to be inferred from models built on data collected before the instruments went dark. Suzanne Dodd, the Voyager project manager at the Jet Propulsion Laboratory, stated the situation without softening. "If we do not power off an instrument on each Voyager now," she said in early 2025, "they would probably have only a few more months of operation before we would need to declare end of mission." The engineering team had been stretching the power budget for years, finding increasingly inventive methods of squeezing additional months from a dwindling reserve. In 2023, they made a calculated gamble on Voyager 2. They disconnected the voltage regulator safety circuit, a protective system designed to guard the instruments against electrical surges, and redirected that small reserved power directly to the science instruments. The risk was genuine. Without the voltage regulator, a power surge could damage or destroy what remained. But the Voyager spacecraft had run on remarkably stable power for decades, and the engineering team assessed the probability of a catastrophic surge as low enough to justify the exchange. The gamble bought an estimated 3 additional years of science from a power budget that had been operating on essentially nothing in reserve. Variable voltages introduce a small risk, Suzanne Dodd acknowledged. The alternative offers a substantial reward in keeping the science instruments running longer. Linda Spilker, Voyager's project scientist, who had kept a sleeping bag under her desk during the Neptune encounter 36 years earlier, described the situation with all the weight of what the mission had accomplished. Every minute of every day, the Voyagers are exploring a region where no spacecraft has ever traveled. That also means every day could be the last. But that same day could also bring the next revelation from interstellar space. So we are pulling out every stop, doing everything we can to ensure Voyagers 1 and 2 continue breaking new ground for as long as physically possible. The team is purchasing time through ingenuity and calibrated risk-taking. Every optimization, every creative adaptation, every calculated gamble adds months or years to a mission that was supposed to run for 4. The engineers maintaining the Voyagers today were children when the spacecraft launched. They inherited machines they did not design, running software they did not write, powered by fuel they cannot replenish. Their job is to keep them alive for as long as possible, with the clear understanding that the fundamental limit is physics itself. Plutonium decays at the rate its half-life dictates, and no amount of engineering ingenuity can alter nuclear physics. Power diminishes. Instruments go silent. And nobody can deliver additional fuel to a spacecraft 15 billion miles away, moving at 38,000 miles per hour in the opposite direction from Earth. The power curve has only one direction, and the only open question is how much science can be drawn from it before it reaches zero. Each Voyager launched with 10 science instruments. The cameras were the first to go, powered down in 1990 after the pale blue dot photograph and the conclusion of the planetary mission. The photopolarimeter and ultraviolet spectrometer followed in subsequent years. The plasma science instrument on Voyager 1 had already failed independently during the Saturn flyby in 1980, a breakdown that would complicate data interpretation for decades. One by one, the instruments that had unveiled the outer solar system with unprecedented clarity were switched off to preserve the dwindling electrical supply. Each shutdown was a permanent loss, a window closing on a class of measurement that could never be recovered, the cosmic ray subsystem that identified the heliopause crossing, the charged particle detectors that recorded the solar wind's final gasp. Every instrument contributed something irreplaceable to our understanding of the space between the stars, and every shutdown removed a capability that no other spacecraft in existence can replicate. By 2026, both spacecraft will operate with only 2 instruments apiece, the magnetometer and the plasma wave subsystem. The magnetometer measures the strength and orientation of the local magnetic field. The plasma wave subsystem measures the electron density in the surrounding medium. Together, they provide the bare minimum information required to characterize the interstellar environment. How strong is the field, and how dense is the plasma? Engineers project that the radioisotope generators will be unable to power any science instrument by approximately 2030. The generators may continue producing enough electricity after that point to sustain the spacecraft's fundamental housekeeping functions, the heaters that keep fuel lines from freezing, the attitude control system that keeps the antenna aimed at Earth, and the transmitter that sends the signal home. That transmitter operates at 23 watts. As the spacecraft move farther from Earth, the signal weakens with the square of the distance. The Deep Space Network's 70-meter dishes can currently detect it. But there is a distance beyond which even those enormous antennas cannot separate the Voyager signal from the background noise of the cosmos. That threshold will be crossed sometime around 2036. After that, the signal will still exist, propagating outward at the speed of light, attenuating with every additional mile. But no receiver on Earth will be capable of hearing it. The communication link between Earth and the Voyagers is among the most remarkable engineering achievements in human history, and it warrants a moment's attention before it disappears. The spacecraft's transmitter broadcasts at 23 watts, approximately the output of a dim reading lamp. From 15 billion miles away, the signal reaching Earth has been diluted by the inverse square law to a power level measurable in billionths of a watt. The Deep Space Network's 70-meter dishes, the largest steerable radio antennas in existence, are the only instruments capable of detecting it. Each communication session requires pointing one of these massive structures at a position in the sky representing where the spacecraft was more than 23 hours ago, because the signal takes that long in transit. The dish gathers the signal continuously for hours at a stretch, and receivers cooled to near absolute zero amplify it above the background noise. The data arrives at rates that would have seemed sluggish in the dial-up era, roughly 160 bits per second from Voyager 1. At that speed, a single high-resolution photograph would require weeks to download. The engineering, telemetry still arriving from the spacecraft fits easily inside a standard text message. And yet each packet contains measurements from the most distant laboratory humanity has ever maintained. The people sustaining this link work around the clock in shifts, coordinating antenna time across 3 Deep Space Network installations in California, Spain, and Australia. Voyager 2 can only be contacted from the facility at Canberra because its southward trajectory has carried it below the horizon of both Northern Hemisphere stations. If the Canberra dish goes offline for maintenance, Voyager 2 falls entirely silent until it returns. The entire communication architecture rests on aging ground infrastructure, institutional knowledge resident in a diminishing group of specialists, and a transmitter in interstellar space that has been running without interruption for nearly half a century, without a single repair. The end will arrive quietly. There will be no scripted final transmission, no elegiac farewell message broadcast across the void. The data stream will simply become too faint to separate from noise. The engineering team will attempt to strengthen the signal, adjust the reception parameters, refine the antenna tracking algorithms, and try again. At some point, the numbers on their screens will dissolve into undifferentiated static, and the staff at the Jet Propulsion Laboratory will acknowledge that the connection no longer exists. The last round-trip communication with Voyager 1 already requires nearly 48 hours. A command transmitted from Earth travels more than 15 billion miles, reaches the spacecraft over 23 hours later, is processed by the onboard computer, and the response begins its own 23-hour journey back, a dialogue that consumes almost 2 full days. By the time the final silence comes, that delay will be even longer, and each exchange will carry growing uncertainty about whether what appears on the screen is genuine data or simply patterns forming in the noise. After the signal dies, both Voyagers will continue at their current speeds. Voyager 1 at approximately 38,000 miles per hour. Voyager 2 at roughly 35,000. They will not decelerate. There is nothing in interstellar space to generate any meaningful drag or resistance. No atmosphere, no friction, nothing opposing their motion in any way. The spacecraft will coast along their current trajectories indefinitely, silent and unseeing, for an interval of time that makes all of recorded human history look like a momentary flash. Their instruments will be locked in their final orientations. The golden records will rest undisturbed inside their aluminum sleeves. The antennas will continue pointing toward a planet whose inhabitants will have long since moved on to other concerns, other pursuits, other crises, long before the spacecraft cease pointing. Two small machines, each no larger than a compact car, drifting through the emptiness between the stars at a pace that would carry them across the continental United States in 5 minutes, aimed nowhere in particular, with nobody listening and nothing ahead. The antennas will keep their orientation toward Earth, fixed on a world that launched them nearly 50 years ago, and that will, sometime in the 2030s, lose the last ability to hear their reply. Approximately 40,000 years from now, Voyager 1 will drift within 1.6 light-years of a red dwarf called Gliese 445, located in the constellation Camelopardalis. Gliese 445 is currently moving toward our solar system, and by the time Voyager drifts into its general neighborhood, it will be among the closest stars to where we live now. 1.6 light-years is roughly 9.3 trillion miles. At that range, the star would appear as a notably bright point in the sky. Brighter than most background stars, but still essentially a point of light. Voyager will not enter that star's planetary system, if one exists. It will pass through the outskirts, a cosmic near-miss measured on a scale where near means trillions of miles of open space between the spacecraft and anything solid. Voyager 2 is headed in an entirely different direction, into the constellation Pavo, traveling below the ecliptic plane. Roughly 42,000 years from now, it will pass near the red dwarf Ross 248, which by that point will rank as the nearest star to our own system. The closest approach distance will be a few light-years, notable on a star chart, entirely meaningless in physical terms. Then, approximately 296,000 years from now, Voyager 2 will pass 4.3 light-years from Sirius, the brightest star visible from Earth. Still not close. Still simply drifting through. These are the nearest stellar encounters either spacecraft will experience for the foreseeable future, and not one of them amounts to an arrival. The emptiness between stars is so absolute that even after tens of thousands of years of travel at speeds that would traverse the continental United States in 5 minutes, the Voyagers will still be alone. They will skim through the edges of stellar neighborhoods without ever entering them, without stopping, without slowing. And one thing must be stated plainly. The Voyagers have not left the solar system. The heliopause marks a magnetic boundary, the outer edge of the solar wind's reach. But the gravitational domain of our star extends incomparably farther. Roughly 1 trillion icy objects orbit in the Oort cloud at distances ranging from a few thousand to 100,000 astronomical units from the Sun. Voyager 1 will reach the inner boundary of the Oort cloud in approximately 300 years. It will not clear the outer boundary for another 30,000 years beyond that. Someone standing in the middle of the United States who takes 3 steps westward has moved proportionally closer to the Pacific Ocean than Voyager has moved toward the true edge of the solar system. The distances defeat every comparison the human mind can construct. Light, traveling at 186,000 miles per second, takes more than 23 hours to reach Voyager 1 from Earth. That same light needs roughly 4 years and 3 months to reach the nearest star beyond our own. The Voyagers, traveling at a small fraction of the speed of light, will need tens of thousands of years to cover distances that light crosses in years. The gap between how fast these machines travel and how far the stars actually are is the gap between human ambition and cosmic scale. The Voyager mission has made that gap visible and comprehensible for the first time in history. Sagan and his team had contemplated that gap when they designed the Golden Record, and they considered one additional possibility. Just before the Voyagers finally went silent in the 2020s or 2030s, one last maneuver might still be feasible. Each spacecraft still carries hydrazine fuel for attitude adjustments. If, in the final days of communication, engineers expended those reserves in a single controlled burn, the spacecraft could be nudged onto a path marginally closer to one of those distant stars. Tens of thousands of years later, the blind and silent machine would drift through the general vicinity of a red dwarf, carrying its golden record through a stellar neighborhood that might just conceivably contain someone capable of finding it. The idea was never executed, but the fuel remains, and the possibility, however statistically remote, has never been formally closed. In the vacuum of interstellar space, almost nothing threatens the Voyagers. No atmosphere to erode them. No moisture to corrode their metal surfaces. No oxygen to rust their fittings. The only hazards are micrometeorite strikes and the gradual bombardment of cosmic rays, and, at the particle densities of interstellar space, both processes operate on timescales of hundreds of millions of years. The spacecraft will eventually erode, but the timescale involved makes geological epochs look brief. The aluminum structures will endure. The gold-plated records will remain intact. The scientific instruments locked into their final positions by frozen actuators will retain their shapes. The thermal blankets may gradually degrade as cosmic rays break apart the molecular bonds in the material, but the structural elements they cover will hold. The Voyagers were designed to withstand the radiation environment surrounding Jupiter, which is far more intense than anything they will encounter in the cold stillness between the stars. The golden records are especially durable. Gold does not tarnish or corrode in vacuum. The engravings on the protective aluminum covers, the symbolic playback instructions, the pulsar map locating Earth's star, all of these will remain legible for hundreds of millions of years. The audio grooves pressed into the copper substrate will survive as well, preserving Bach's Brandenburg Concerto, Beethoven's Fifth Symphony, the sound of a mother welcoming her newborn into the world, and greetings, recorded in 55 languages, in a format decodable by any civilization that has figured out how to build a phonograph. Long after every building on Earth has crumbled, long after every human language has gone extinct, long after the continents have assumed shapes that no living person would recognize, long after the species that built these machines has transformed into something unrecognizable or ceased to exist entirely. The Voyagers will still be out there, carrying the sounds and images of a world that no longer exists. They may, in the most literal possible sense, be the last physical evidence that a civilization called humanity once occupied a small blue planet orbiting an ordinary star in an unremarkable arm of the Milky Way galaxy. Two small machines drifting in complete silence through an emptiness that extends in every direction for light years, carrying golden records that nobody may ever retrieve, aimed at nothing in particular for a duration that defeats every unit of time humans have ever devised. The pyramids of Giza are roughly 4,500 years old. The Voyagers will not approach their first stellar neighborhood for 40,000 years. By the time Voyager 2 drifts past Sirius, nearly 300,000 years will have passed, a span longer than the entire prior existence of the human species on this planet. The machines will outlast everything else we have ever built or known. They were constructed to survey a solar system, and they will end as relics drifting through a galaxy that may contain no descendant of the creatures who assembled them. Sagan grasped this when he helped create the records. He knew the spacecraft would likely outlast everything. The launching of this bottle into the cosmic ocean, he wrote, says something very hopeful about life on this planet. The hope was never that someone would find the bottle. The hope was in the act of throwing it. Here is what the Voyager journey actually reveals when you trace the full arc from launch to silence to eternity. Two spacecraft were assembled with 1970s technology, dispatched during a planetary alignment that will not recur for 176 years, and sent on a tour of the outer solar system that generated more discoveries than any mission before or since. They found active volcanoes on a moon that had every reason to be dead. They found evidence of an ocean under the ice of another moon that may contain life. They photographed storms with winds 8 times more powerful than the worst hurricanes ever recorded on Earth. They documented ring systems around every giant planet, geysers erupting from surfaces colder than anything on our world, and an atmosphere denser than our own, wrapped around a moon smaller than Mercury. They photographed their home planet from 4 billion miles away, and that photograph changed the way a species understood itself and its place in the cosmos. They crossed a boundary no human creation had ever reached, and on the far side they discovered that the space between the stars carries a quiet, constant sound that has been playing since before our solar system formed. And now, after all of that, after rewriting the textbooks of planetary science, after producing the most resonant image in the history of space exploration, after crossing a threshold no human object had ever crossed, the Voyagers are dying. 4 watts drain away every year. The instruments that made those discoveries are going dark one by one. Within the decade, both spacecraft will fall silent, and humanity will have nothing functioning in the space beyond the inner solar system. After the silence comes the drifting, the long, cold, infinite drift. 40,000 years to pass near a red dwarf that will take no notice of them. 300,000 years to drift past the brightest star in our sky at a distance that renders the encounter meaningless. Millions upon millions of years of cold and darkness, carrying golden records loaded with whale songs and bird song and greetings in languages that were already dying before the Voyagers left Earth. The terrifying truth is the scale. After nearly 50 years of uninterrupted travel at 38,000 miles per hour, a speed that would carry you from New York to Los Angeles in roughly 5 minutes, humanity's farthest creation has barely moved relative to the distances that separate the stars. The numbers stop making sense at this scale. Miles, kilometers, astronomical units, light years. Every unit of measurement becomes inadequate when trying to express the sheer vacancy between one stellar system and the next. The nearest stellar system remains inconceivably distant. The edge of the solar system's gravitational hold is hundreds of times farther than where the Voyagers are right now. The galaxy is so unimaginably vast that the fastest objects our civilization has ever produced are, in cosmic terms, stationary. And yet these two small machines did something that nothing else in the entire history of our civilization has ever managed. They left. They crossed the boundary. They heard the hum of interstellar space and transmitted the recording back to us across 15 billion miles. They carried our music and our voices into a silence so profound that it will take 40,000 years to reach the nearest potential listener, if it reaches anyone at all. The universe is large beyond comprehension, cold beyond endurance, and empty beyond imagination. Two machines the size of a small car, drawing less power than a reading lamp, carrying the sounds of a world that may not survive long enough to receive any reply, traveled further into that darkness than anything our species has ever sent. The engineers who built them are mostly gone now. Ed Stone, the project scientist who presided over the mission for more than 50 years, died in 2024 at age 88. Many members of the original team have retired. The graduate students who watched the Jupiter images arrive in 1979 are now in their 70s. A new generation sustains the communication link. People who were not alive when the spacecraft launched, working with systems they did not design, keeping alive a connection that spans 15 billion miles of open space. The Voyagers are still out there. They are still moving. And for a little while longer, perhaps a few more years, perhaps into the early 2030s, they are still talking to us. Every day the data arrives, traveling for nearly 24 hours at the speed of light, carrying measurements from the most distant laboratory humanity has ever maintained. Every day could be the final one. And every day that it is not is another day that two small machines, alone in the dark between the stars, remind us of everything our species is capable of when we commit ourselves to reaching the very edge of what is possible. That is the legacy of Voyager. Not the data alone, remarkable as it is. Not the photographs, as breathtaking as they remain. The legacy is this: we built two machines with the knowledge and tools of a single decade, pointed them at the darkness, and they are still going, still transmitting, still carrying our voices forward into a silence that existed long before we did, and will continue long after every trace of us has gone. If that is not worth staying for, nothing is.